most active volcano.
For 30 years, lava has been spewing out a line of craters engulfing homes and property. In 2008, that crater exploded into action, forcing the closure of this park.
But does science know enough about volcanoes to keep us safe? This is Volcano Live. Glorious morning here in Hawaii Volcanoes National Park. We are coming to you live from the middle of the Pacific. Let's just remind you where exactly we are now. We're on Big Island at the bottom of the Hawaiian archipelago, right there on the rim of Kilauea. As I said at the beginning, the world's most active volcano.
Now, yesterday we were at the coastal community of Kalapana, but what we did was we packed all our gear up, we moved the trucks there. You can see us moving across them, taking little mini Winnie all the way up here to the summit, to this, what's behind us here, which is the house of the eternal fire, Halimau crater. Now the thing is, that giant plume of gas coming out there means that we can't get any closer than this. Those fumes are toxic. It also means it's hard to see into the crater, so we get cameras that's going to show us the latest pictures. You can see there's a camera at the top showing just what it looks like normally, and then the thermal one below shows the lava kind of churning away, and the heat there is extraordinary, several hundred degrees Celsius. So that's what's right behind us. And you can have your own personal view of the Kilauea lava lake whenever you like by going to our website, bbc.co.uk/Volcano Live. We've got various links to various webcams on active volcanoes throughout the world. And also, if you go onto our website, you can join a web chat with Professor John Blundy from the University of Bristol. He will be answering your questions throughout the show and after the programme. Now, we have been looking really at how volcanoes work throughout this week, haven't we? That's right. I mean, over the last 3 nights, really, and then today as well, we're looking at how volcanoes work and really, the processes that cause them to erupt. But tonight, we're going to explain just how good are we at working what volcanoes like this and others around the world have got in store for us. Tonight, a volcanic tragedy. Oh my God, look at that! I come face to face with the 2,000-year-old victims of Mount Vesuvius in Italy.
I meet an Icelandic giant which could dwarf the eruption of Eyjafjallajökull.
Ed Byrne gets creative with some balls and a rubbish bin to build a supervolcano.
And the volcanologists who go to the end of the earth in pursuit of the perfect volcano. Now, our understanding of volcanoes has vastly improved in modern years. We know where all the active volcanoes are and we know why they erupt, but the thing that really still scuppers us is when they're going to erupt and for how long.
Well, that's right. That's one of the big challenges, is working out precisely when they're going to erupt, how big that eruption is going to be, and as you say, how long it's going to take. That's some of the key questions. And what we're going to look at tonight is if you like, the tools of the trade. How do we know, if we take a volcano like this or other ones around the world, how do we know, when trouble is brewing?
Well, later on we are going to meet Professor Steve Anderson and his team, who have been using cutting-edge technology to produce 3D images of the crater behind us that have never been seen before. So that's something very much to look forward to.
Well, scientists from the Hawaiian Volcano Observatory, we can see it just over there, just perched right on the edge of the crater, and those scientists are looking for telltale signs of activity. And one of the things they're looking at is the gas. In the weeks before the eruption of the Halimau crater, the gas levels just went through the roof. And what it means is that constantly billowing gas plume there isn't just a health hazard for us. It's actually one of the real indicators that, as I say, trouble's brewing. Let's have a look at this film.
I'm Tamar Elias, and I work at Hawaiian Volcano Observatory monitoring and studying volcanic gases. Gases can give us information on what's happening beneath the volcano. It can give clues as to what the behavior of the volcano might be. The volcanic coming out of this vent has a variety of particles and gases. The visible part is mainly water vapor and tiny particles, but there's also a hatful of gases, including sulfur dioxide gas. And there's also carbon dioxide, hydrogen fluoride, hydrogen chloride, a little bit of carbon monoxide. It's a cocktail of gases. Volcanic gases are dissolved in magma, and different species of gases bubble out of the magma at different depths or different pressures. One of the gases that's particularly useful is sulfur dioxide, or SO2. The sulfur dioxide emissions rise and fall with the activity of the volcano because it's emitted very close to the surface. We actually use a small spectrometer, an ultraviolet spectrometer system called the FlySpec, to measure how much sulfur dioxide gas is coming out. The ultraviolet spectrometer in this system basically is measuring light. And conveniently, sulfur dioxide gas absorbs ultraviolet light very effectively. And so we can use that property to measure how much, or calculate how much SO2 gas is between us and the sun. We drive beneath the plume, and we measure the concentration of sulfur dioxide above us. It can be reasonably extreme. You would smell the SO2, you would taste the SO2, and you would feel it irritating your throat. But we use a gas mask in the car. In 2008, we started to see an increase in the sulfur dioxide gas that was being emitted here at the summit. And we started measuring amounts that were unprecedented in our era of making these measurements. And it let us know that an eruption could occur. And in March of 2008, this vent opened up. It's amazing to be on Kilauea during this era. I think as humans we believe that scenery is rather static. I think that working here you can see that the whole landscapes can change very quickly.
Tamar mentioned the gas level changes that accompany that 2008 eruption, and just to put that into context, a normal baseline emission of sulfur dioxide from that volcano is about 200 tons a day. But just prior to the eruption of that lava lake, those levels went up 10 times, 2,000 tons a day. And that hole in the ground is the biggest sulfur dioxide polluter in the US. Now, as we know, every so often Kilauea has these tantrums, and somebody who knows that firsthand is Mark Patrick, geologist at the H3O. Now, Mark, I'm going to show some footage now of an eruption of fire fountain that went on in March 2011. Just if you see it there, you were there. What was it like? In fact, on the two people there, you're on the left.
Yeah.
What was that like?
It was spectacular. It was really the highlight of my time here at the Hawaiian Volcano Observatory.
You don't seem too close.
No, we're not actually, and that's because it was so hot. It was just keeping you at this distance. It was like standing in front of an oven.
Now you look as if you're kind of, I don't know if it's the right word, enjoying it there. But of course, most of your work is trying to second guess when the volcano is going to be active. And this week we've seen you monitoring lake levels. We've seen Wes looking at earthquake tremors, and Santa Marla sniffing out the gases. But you guys all work together, don't you?
Yeah, absolutely. And that's one of the benefits of working at the observatories. We have all those specializations based right there. So I can just go down the hallway and talk to someone who's a seismologist or a gas specialist. And you really need to pull all those together to get the full picture.
The other thing I've been really impressed with, I must admit, is that you put most of your data out on the web, and you've got webcams where you encourage the public to come and have a look at the volcano. Are you not a little bit concerned that all that data will turn people into kind of armchair volcanologists, interpreting data, maybe misinterpreting the data?
Yeah, I think years ago when more data started to be put on the web, there was a concern of that, but it hasn't really been a problem, and it's greatly outweighed by the fact that the benefit of having the public involved and getting them interested in the activity.
Now, I guess every so often you must see the gas or the earthquakes, maybe all the ground tilts starting to tell you that trouble's afoot. And how does that work? At some point, you presumably have to get the park officials in and say, "Look, guys, we think an eruption is likely." That must be a really tricky judgment call.
Yeah, it is. It can be. The trickiest part is, well, we have these instruments, and we can track very well when things are ramping up. But the big question is, what's going to be the breaking point? And but we look at the geologic record for past insights on that, and we look at all the data we can.
And I guess that's a problem the world over with those people observing volcanoes.
Yeah, absolutely. It's a universal challenge at volcanoes to know. You can track when things are increasing and building up, but it's knowing that critical point is a challenge.
Okay, thanks for that, man. One of the things that's interesting is that monitoring gives you this really short-term baseline of a few decades. Sometimes that's really not enough to capture the behaviour of a volcano, and that's where history comes in, because history gives you that longer perspective on what the capacity of a volcano is for destruction. And that's something that I learned when I went off to a Roman town in the shadow of Vesuvius. Mount Vesuvius in southern Italy. It's responsible for one of the most famous natural disasters in history. In 79 AD, Vesuvius erupted in spectacular style, blasting out a lethal cloud of ash and molten rock. The cloud grew to 30 kilometres in height, and the wind blew it straight to the Roman city of Pompeii. 3 meters of ash and rock rained down on Pompeii. Buildings collapsed under the weight, and hundreds of people were engulfed and suffocated. Today, their entombed bodies still lie exactly where they died. The ash cloud swallowed Pompeii so quickly, the citizens wouldn't have known what hit them. But here in the ancient city of Herculaneum, 15 kilometres to the west, people would have seen the horror unfolding. The wind had blown the ash cloud to the south, towards Pompeii, so from Herculaneum they would have had a clear view of Vesuvius. It's hard to imagine what must have gone through their mind. Their mountain, which hadn't even been recognised as a volcano, was exploding into life. A huge black cloud filled the sky, and the ground was racked by earthquakes. It must have seemed like the end of the world was coming. But unlike their neighbours in Pompeii, the people here had time to run for shelter. These homes and buildings were found abandoned. The people had fled, but that didn't mean they'd escaped. When archaeologists excavated these ancient chambers, they made a shocking discovery. Oh my God, look at that!
So in each of these chambers were found 30 to 40 victims of the eruption.
So are these real skeletons?
These are casts, but they are just the real exact copy of the victims as they were found.
What's the story of these skeletons then? What happened to these people?
At the very beginning of the eruption, the town was shocked by several earthquakes. They thought these arcades could be a safe place, but actually this was not a good place to be for the eruption.
Sheltering here was no use. because the earthquakes and the huge ash cloud filling the sky was just the first phase of the eruption. Then came the pyroclastic surge, a lethal torrent of ash and gas that had been superheated to 500 Celsius. It tore through these streets at 150 kilometers per hour, obliterating everything and everyone in its path.
Many skulls were exploded due to the direct effect of the heat on their bones and also due to the overpressure induced by the boiling brains.
Boiling brains?
This skull looks as if it's been crushed, but you're saying that it's actually exploded out because their brains have boiled?
Yes.
What a way to go.
So when the pyroclastic surge comes through the city, there's nothing which could protect them.
After such a devastating natural disaster, you'd think no one would ever want to live here again. But where once stood a Roman settlement of 5,000 people, there now stands a modern town of 50,000. And the people that live around here today face the same threat as the citizens of Herculaneum, because Vesuvius is still an active volcano. In 1906, an eruption claimed over 200 lives. And in 1944, 28 people were killed when Vesuvius blasted ash and rock over nearby towns and villages. These eruptions were relatively minor. A bigger one would be far more devastating, because the lethal pyroclastic surges from a major eruption could easily travel 20 kilometers or more. And that means they could reach the city of Naples, threatening the lives of over 1 million people. That's why today, Vesuvius is one of the most heavily monitored volcanoes on the planet. Here at the Vesuvius Observatory in Naples, scientists use the most sophisticated technology available to keep watch over the volcano 24 hours a day. State-of-the-art instruments positioned all around the crater feed information back to the control centre, so the scientists can monitor the volcano's every move.
There are tens of these stations all around the volcano, and they include different devices like this thermal camera, which allows us to detect any change inside the crater in terms of temperature.
So that's like hot gases and hot fluids rising to the surface.
Then there are gas monitoring system and seismic stations under the ground. Yes.
So underneath this station here, there'll be a seismometer, will there, recording seismicity in the crater.
Seismicity inside the crater.
By monitoring seismic activity, the temperature of the crater, and the composition of volcanic gases, scientists will know when magma deep inside a volcano moves towards the surface, a key indicator that an eruption is imminent.
So only by merging data collected by all these instruments, we can have a picture of what happens beneath the volcano.
So could a big eruption like the size of 79 AD, could that happen again?
Yes, of course. Our research and instruments have demonstrated that there is a very wide magma chamber, as wide as 400 square kilometers, with a depth in the order of kilometers. So there is magma available for tens to hundreds of large-scale eruptions, like the Pompeii one.
These high-tech instruments can help scientists predict when the next eruption might occur, but they can't stop it from happening. So the danger facing the people who live here today is as high now as it was in 79 AD. The difference is, today we think we understand this volcano by combining modern scientific techniques with evidence of past eruptions, like the one in 79 AD. Scientists know what this volcano is capable of and believe they can read its warning signs. But that is only half the story. Because the question is, when those warnings come, will the authorities down there be ready? Can we really evacuate all these people safely? That, perhaps more than the science, will be the really tricky part.
So is there a plan if it does happen? Do you think the authorities can react and evacuate people safely?
Yeah, there's a plan. I mean, the assumption is that the eruption's not going to happen suddenly. There's maybe 2 weeks' notice, either from gas or earthquakes or tilts or something like that. But the plan is that they're going to evacuate the red area. And the red area is the area's got the pyroclastic flows, which we saw so deadly.
Okay.
But the trouble is that 600,000 people live in that red area.
Wow. That's extraordinary. So, I mean, just the physical, how do you get all those people out?
Well, if they have 2 weeks, the plan is to mobilise, it's a huge mobilisation, mobilise 16,000 police and soldiers to get 80,000 people a day out on 80 ships, 40 trains, 4,000 cars. But here's the thing, they might not have 2 weeks. They might have as little as 72 hours.
Well, I was going to say, I mean, that's an awfully big assumption, isn't it? To say, oh, well, we'll definitely have 2 weeks and we'll have it all organised.
Well, 72 hours is what they might have. The other thing is, they may have to evacuate far more because they also might have to evacuate areas where the ash cloud is going.
Right.
Because they don't want another Pompeii.
Yeah.
So that might be, and that's a whole other pile of people. The other thing is that the assumption of the earthquake size is that it's based on an eruption that's smaller than AD 79. So if it's going to be an AD 79 huge eruption, then all of those numbers I've just said have to increase.
Wow. So really, they're not planning for the worst. They're planning for the kind of best case scenario.
But I have to say, I mean, one of the things is, at least Naples has a plan.
That's true.
Because there's other volcanoes around the planet that have got an equally important threat.
Yeah.
And yet don't have such a plan in place. It's quite scary.
It is quite scary, and it's not just scary in places like Naples, it's pretty scary for the people who work here at the Hawaii Volcanoes National Park. There are 5,000 visitors a day that come here, unsurprisingly. I mean, when you see that, don't you want to book your ticket? Jim Gale, you have the unenviable task of making sure that people have access to this wonderful park, to these wonderful volcanic sites, but also being safe. Now, you've got the HVO, the scientists perched over there. Presumably you guys work a lot together.
Absolutely. They're part of our team. They provide us with the most up-to-date science in the current eruption.
And how do you measure what they're telling you in terms of, you know, how you then need to react as far as the public are concerned?
Well, the most important part is keeping the visitors safe.
Yeah.
Out of the dangerous gases or away from things that could cause harm or have an unpleasant vacation. Mm-hmm. So those are our major concerns. So if there's a shift in wind or something like that, that's why we needed to close the road over there, because the wind blows that direction and the gases are too much.
So there used to be a road that went all the way around the crater, didn't
That's
it?
right. Mm-hmm.
And you've closed that now because
Correct.
that's the prevailing wind. It blows that gas over there. So you're kind of constantly monitoring the various conditions around the park and reacting accordingly.
Exactly. Yeah.
Has there ever been a time where you have had to say, close the park, nobody in here?
For one day, we had a forecast from the scientists that the plume was going to shift back.
Right.
And so we needed to close the park because we were so afraid. We didn't know what was going to happen, and we needed to protect the visitors. So for that one day, we closed the park to make sure that visitors would not be in harm's way.
So what the scientists were telling you was that plume would come in this direction, basically flooding the whole area of the park.
Right, because right now we're in good wind, and so we're upwind of the vent. But the weather was shifting, and it was our first time that had ever happened, so we didn't know exactly what was going to happen.
And I mean, what was the sort of outcome of that? Were people kind of furious? Did they understand what you were doing?
Well, we learned a lot, and what we learned is that there's always an open area of the park. You know, we can take people to a place that's open.
Right.
But one of the key things we learned was that people changed their travel plans.
Wow.
They canceled their airline reservations, they canceled their hotel.
So the implications were not just for the park, but you had a ripple effect on the whole island, really.
Absolutely.
Because the island presumably depends quite a lot on the economics that you provide here.
Right.
Not an easy decision to make then, but presumably you have to put safety first.
Absolutely, because that's the whole purpose, is to provide accessible, approachable visitor experiences with viewing the lava, but not at the cost of someone's health or safety.
Well, I don't envy your job, Jim, but I certainly envy where you work. Thank you very much. It's been a real pleasure working with you this week. Now to Iceland. Iceland is one of the most volcanically active countries on Earth, and we all do remember that eruption of 2010, Eyjafjallajökull, that caused chaos in all our lives. But actually, as I learned when I was in Iceland, that's nowhere near the biggest volcano there, and it's its next door neighbour that is really causing people concern. Here in southern Iceland, this mountainous terrain has been shifting and changing for thousands of years. The scale of this landscape is just astonishing. There are huge crevasses that have opened up as the glacier sweeps down the side of this mountain. But of course this isn't a mountain. This is a volcano called Katla. Lying beneath the ice, Katla is one of the largest and most active volcanoes in Iceland. When Eyjafjallajökull erupted just a few miles from here in 2010, there were also suggestions that a big eruption here is now overdue. To find out whether that's true, we're leaving the helicopter behind and hitching a ride in specially adapted jeeps to get us across Katla's huge and treacherous ice cap. Why is it necessary to have such big tyres? Is it just to make you feel a bit more macho?
A little bit like that. No.
It's a vast ocean of ice, and we drive for several miles without seeing a thing. Along the way, we're joined by a snowmobile. It's a dramatic entrance, but thankfully this is no Bond villain. It's Dr. Benio Fageson, one of Iceland's leading volcanologists. He leads us to a rocky outcrop rising out of the icy plain, the highest point for miles around.
We are actually at the edge of the caldera rim.
Right.
The caldera is a depression that is formed when a magma chamber is emptied.
So what we're looking at here is snow and ice covering that kind of classic volcano crater. And the caldera stretches in which direction?
If you look around here, we see the edge of the caldera rim.
So all high points?
The high points here are at the edge of the caldera rim, all the way around.
So, I mean, it's absolutely enormous.
It's enormous. It's about 10 kilometers diameter.
And how thick is the ice on top of it?
About 750 meters.
Wow. Calderas are the huge craters found at the top of the very biggest volcanoes in the world. They're formed by what are known as super eruptions, and Katla's caldera was made in exactly that way. The explosions that created it several thousand years ago were 50 times bigger than Eyjafjallajökull in 2010, depositing ash layers in Russia, some 2,000 miles away. Fortunately, not every eruption here is quite that big, but Katla has seen plenty of activity in the last few hundred years. So how active is this volcano?
Well, it has been erupting roughly once or twice every century.
Okay, so the last time it had a great eruption?
It was in 1918. It was about 3 times bigger than the Eyjafjallajökull eruption.
In 1918, heat from the eruption melted part of the glacial ice in Katla's caldera. an enormous flood was unleashed, ripping huge chunks of ice from the glacier and carrying them down towards the coast. That is almost a century ago.
Yes, yes.
So does that mean it's kind of overdue?
Well, I mean, no, I wouldn't say that. I mean, volcanoes aren't overdue. They change patterns on a regular basis, or irregular basis, actually. And they are irregular and complex things. It might erupt in 10 years. It might erupt in 50 years. It might erupt in a few weeks.
Okay, should we get this job done then? The length of time between eruptions at Katla varies a lot, so the only way to forecast exactly when the next eruption might be is by carefully monitoring its behaviour. Benny uses extremely sensitive GPS instruments, and if the ground here moves by just a single centimetre in any direction, that movement will be recorded. It looks, to the uninitiated eye, that it's moving quite a lot.
Yes, it is. It is moving quite a lot. What we are looking at now is volcanic unrest, and that's sort of a long-term indicator that something could potentially happen, and it could potentially happen at short notice.
But Benny is used to seeing chaotic ground movements in this area. What he's really looking for is evidence that shows whether the pressure is building in Katla's magma chamber, deep beneath our feet. How does magma accumulating kilometres below us, presumably, how does that affect a GPS instrument right up here on the surface?
You have a magma chamber below a volcano,
Yeah.
and there is magma coming into that magma chamber. It increases the pressure in the magma chamber, so you're basically increasing it in size.
Right, so
it's like blowing up a balloon. So you see it on the surface.
Okay.
You see an uplift and away.
So Benny won't issue any warnings until he sees clear movement up and away from the magma chamber over a period of days or weeks. Only that would suggest that Katla is building up to a really big eruption. In the meantime, Katla continues to rumble away, and just last year a small episode of geothermal activity was registered beneath the ice cap. Now that geothermal activity of 2011 heated up the ice and caused a flood of water to come pouring off the volcano and down this river valley, taking out the bridge and causing mass devastation as it made its way to the sea. The flood was a smaller version of the deluge in 1918. It's a reminder that even between big eruptions, Katla can still pose serious problems for those living nearby, making it vital that we continue to monitor this slumbering giant. It is an incredible country, Iceland, and it is incredible really how the people there kind of cope with this volatile home that they've chosen to live in. I have presented a 1-hour special on Iceland and its volcanoes, which will be going out on BBC Two a little bit later in the year, we think in the autumn, so keep your eye out for that. But it does seem to me, Ian, that this predicting what a volcano is going to do and then telling people what your prediction is sort of fraught with problems and controversy, really.
Yeah, that's a real tricky business. I mean, if you see the signals and raise the alarm and nothing happens, then, there's all sorts of disruption and panic. On the other hand, of course, if you see the signals and don't raise the alarm, then you get it in the neck because there's a disaster that ensues. So that's one of the reasons why volcanologists especially have moved away from the idea of trying to be predictive and going for forecasting. In other words, to say something about their expectation of the likelihood of an eruption, say in days or weeks, in large part so that people can be prepared and also maybe take their own cue, maybe leave on their own...
make their own decisions, feel informed about making their own decisions. Well, all this week we have had some very up-to-the-minute information from the Smithsonian to tell us about which volcanoes have alerts, basically. They're all active, and they're all volcanoes that people should be keeping an eye on. Here they are. This is the latest, all the volcanoes that have alerts on in the last 24 hours. Many of you have emailed to say, why are you missing out New Zealand? New Zealand has got volcanoes. It has, but none with alerts on, which is why... Yes, it's not being ignored, we promise. But let's have a look, because one has been causing a bit of...
One in Ecuador, Tunga Nueva. That is, if we can have a look at the webcam, what we see is there's been a lot of some mild plume activity from, there it is, here we go. It's a lovely volcano. It's hard to see what's behind that cloud, but we know that there's been some plume activity that's been coming up. But the real problem with this one is it's so close to Quito, which is the capital of Ecuador, over 2 million people there. So, even a moderate eruption from this volcano could have a big devastating effect. So, a huge one to watch over the coming days.
And the other one, again, that we looked at earlier in the week is in Japan, one that you know quite well.
Sakurajima, this is just in this island here in southern Japan. If we can have a look at the webcam, what the latest is on that.
That's going to tell us a lot, isn't it? That is the problem. You can keep an eye on these webcams as well by going to our website, but you don't always get the greatest
Well, I have to say also it's night time in Japan at the moment, so if you go there it'll be black. But if we can have a look at, I was there in 2005, just to give you an idea. This is Kagoshima, 1 million population city. Here's the volcano here, and this is within striking distance of big pyroclastic flows. But I went across to a community here right underneath it, and I went into a school to see the kind of protocols and practices they have. And if we can have, so what is the school kids, and these are primary school kids, every Friday have a drill. They rush out of the classroom, they get their protective hard hats and for the ash, and they've got their gas masks, and they run down the stairs and they assemble in the playground outside where they're kind of checked out. There's a lovely photo, it's my favourite. Look at these. Every Friday this happens, and you can't see this, but just above the school here is the volcano. The point is, in many of these communities around the world, although these people are drilled and prepared for volcanoes in their midst, and I think that's what in the UK we kind of forget about.
That's it, because we're not living in a sort of in a volcanic landscape, so we tend to sort of perhaps build them up more than people who do. Which brings us neatly onto our questions. Thank you for all the questions that you've sent in this week. We've got a fantastic amount. First one from Alec, who's in Rio, and he is going to Vesuvius this October with his school, and he wonders, are there any laws on taking samples of volcanic rock from Vesuvius and back home to the UK?
Yeah, that's a great question. I think there are. I think there's many of these volcanoes that are protected sites, and I think you need to check, but I don't think you can. When I was there, I didn't take any because I was certainly worried. Here, you're definitely not allowed to.
No, you're absolutely not, because there is a goddess called Madame Pele who lives inside the volcano, and it is deemed hugely bad luck and bad form to take a rock from here. And in fact, the post office in Hilo, just here, receives hundreds of packages of lava being returned, because obviously people have had bad luck and they thought, it really is true, I've got to send it back to Madame Pele. Quickly on to Robert Crawford, who's 13, he's in Bearsted in Kent. He wants to know what the people living in Pompeii thought the volcano was if they didn't think it was a volcano.
Well, this is interesting. The Greeks, before the Romans, knew it was a volcano. They saw it erupt, but it hadn't erupted for centuries. So for the Romans, it was just a mountain.
Right, yeah, good point. Caroline Lomas in London, she wants to know, this is a very good question, can one volcanic eruption trigger a chain reaction? Now, I know this was something in Iceland, but people were worried that Eyjafjallajökull could indeed trigger Katla to go off. It turned out that they have separate magma chambers, they couldn't, but is there a case where it could?
There can be connections, stress conversations between them, and also between earthquakes and volcanoes. And one that's nice here is between Kilauea and Mauna Loa here. Now, when Kilauea is really active, Mauna Loa tends to be quiet. When Mauna Loa kicks up, Kilauea goes quiet. So it's about different magma chambers responding to each other.
John Howard wants to know, are there any active undersea volcanoes? Very quick answer to that, John.
Lots and lots. Probably the most common, but we just don't cause volcanic alerts generally.
Spencer Liggett, very quickly from Cardiff, he says, if magma is being released to the surface and forming new land, does that somehow mean that the Earth is
And it
shrinking?
kind of shrinks and it can drive through it. No, because as that magma builds new land, there's a plate tectonic, so this conveyor belt, it sends it down subduction zones, and that gets taken back into the mantle. It's a beautiful recycling system.
Thank you, as I say, for all of you who sent in your questions. I want to make a quick mention. Jack, age 7, Andrew Dara, who's 8, Alex Swan, who's 16, and lots of lots of other people have said they love to be volcanologists.
Brilliant.
And they want to know how. Talk to him.
Well, this is one of the points, because actually this week we've talked lots about technology, all this high-tech stuff, but what's been an absolute joy for me is to watch the films where you really see the people that study them, and also the lengths, the extremes they go to get their data. And one that exemplifies that passion and commitment for me more than any other is Clive Oppenheimer. And this week, Clive went to Antarctica.
I'm interested in volcanoes, how they work, why they erupt in a particular way. If we want to be able to predict eruptions, that's obviously one of the key goals of volcanology. We really need to understand how volcanoes work. So we need to find laboratory volcanoes where we can make very detailed measurements. Mount Erebus in Antarctica is the world's southernmost active volcano. It is over 1 million years old and lies in the West Antarctic Rift System. Every December, I make the epic journey to Mount Erebus with a team of a dozen scientists and students to live and work for a month. The main reason I go to Erebus is to measure the gas emissions from the lava lake. They're really like messengers from the Earth's interior. It is a big project to go there and you need a lot of time, but the scientific rewards there are just phenomenal. I've been coming here to the very edge of the world for the past 9 years. We fly to New Zealand and then on to McMurdo on Ross Island where we pick up provisions, then finally take a helicopter the last hop of Erebus. We go to an acclimatization camp, which is at the head of a glacier called the Fang Glacier, so we call it Fang Camp. Going from sea level to high altitude, you suddenly realise that you're in Antarctica, and the views across the sea ice are spectacular. The camp here is pretty basic, with just a few tents and a bucket. We try and acclimatise at least for a couple of nights in Fang. We travel by skidoo up to our main field camp. This is my home for a month every year. It's a truly extraordinary place, and it's a bit like landing on Mars. We set up camp next to 2 permanent huts, just an hour's walk from the summit of the volcano. Typical temperature in the camp would be about -30 Celsius. If the wind is up, even if it's just a few knots, then you really start to feel it. And working up at the crater, particularly if you've got to take your gloves off to fiddle with a screwdriver or something, you lose fingers in seconds. The cold and altitude have also led to 2 helicopter crashes on Erebus over the last 30 years or so, but luckily everyone survived. It's just a reminder of the dangers of being up in that part of the world. We do still sleep in tents. It's not one sort of nod to the heroic era of Scott and Shackleton, so you can have Scott tents. And they're not blackout tents, so it's a little bit difficult coping actually with the daylight that you have 24 hours a day. Life is harsh here, but studying the volcano makes it all worthwhile. Depending on the weather, we try to get up to the crater rim every day when we monitor its activity. The crater is half a kilometre across, and the lava lake here at Erebus is one of only 4 major lava lakes in the world. I'm here to measure the gases in the volcanic plume. measuring the composition and flux of gases enables me to understand how the volcano works and why it has a lava lake. My favourite device on Erebus is my FTIR, which is Fourier transform infrared spectrometer. And it measures anything that's coming out of the volcano. And there are 7 different gas species that we can measure. And the nice thing is we can measure those gases every second with very, very high accuracy. And that's great for following subtle changes in the behaviour of the volcano and very rapid changes. And the gas emissions themselves are one of the best messengers to tell us where is magma in the crust, how deep is it full of gas or not, is it on the rise, is the volcano gearing up towards a different kind of eruption. The ice caves are one of the most stunning features on Erebus, and they're a bit of a puzzle actually as to why they're there in the first place. They're connected with the heat that's being lost from the volcano and also from gases. We know that some of the caves are very rich in carbon dioxide in their atmospheres. So we think possibly they're connected also with the magma point system of the volcano. So we have an active research program trying to understand their formation and origins. A very exciting aspect of Erebus's behaviour is that it explodes from time to time, unlike other lava lakes in fact. We use the camera to observe the volcano when we're not up in the room, of course, but also to capture explosions. And some of them are very dramatic. All the lava in the lake is expelled, and you see the lava bombs flying out. Sometimes they almost take out the camera itself. Each year, we look for new lava bombs to sample so that we can analyse them back in the lab. There's still a huge amount we have to learn about Erebus, but what we're finding out here will help us to understand other volcanoes across the world. One of the things that makes Erebus a fantastic place to work is it's very cold and it's very dry. Erebus is a great natural laboratory to study how a volcano works, and that has all sorts of generic lessons for understanding volcanoes worldwide. I think the measurements that we've made of gas emissions at Erebus rival anything else I've seen for volcanoes around the world. We've got really, really detailed data. We've been going there year after year. We measure gas emissions every second, and that's really enabled us to piece together a lot of the detail of how the volcano is plumbed into its network of magma bodies and feeder pipes below the surface. It's an exceptional place to live, and it's just amazing privilege to get to work there and to get to go back as well.
So there you are, all you would-be volcanologists. How would you like to go down to Antarctica to study volcanoes? Now, Erebus has one of only 4 permanent lava lakes in the world. One of the others is right here on Big Island in Hawaii. And I'm here with Dave Finnegan, who is a research geologist. Dave, thank you very much indeed for joining us today. You have been spending the last months and weeks actually mapping this lava lake using this extraordinary piece of kit. Can you just talk me through this, because I've never seen anything like it?
That's right. So this is actually what's called a ground-based LiDAR system, and basically what it is, it's a laser beam mapping system that allows us to do high-precision terrain mapping at centimeter scale at long distances. So it's a unique operation that allows us, instead of just taking pictures, we actually can map in 3 dimensions different parts of the volcano.
And why is that important? Why is it important to have that sense of distance? Surely you need to get up close to really understand what a volcano is doing.
Right. So what's really important is that we do need to get close, but 9 times out of 10, we can't get there. It's too dangerous, the gases, the heat, as some of the other speakers had said, that it's important for us to have a standoff system that allows us to get precision information at long ranges. And these systems allow us to do that. They allow us to map in 360 degrees at very high precision without putting people in harm's way, but coming up with the science information that we really need.
Well, I'm going to go and have a look at the results of your work with this extraordinary machine with Dave's colleague, Professor Steve Anderson from the University of Northern Colorado. Good morning, Steve.
Good morning.
So an impressive piece of kit, presumably giving you some impressive results. Before we have a look at what you've been able to produce over the last few weeks, let's just have a look at the view of the crater that we are more used to seeing. I mean, it's a pretty good view, but I suppose from a scientific point of view, a little vague. It tells you some things, but not quite enough to be analytical.
Right.
Beautiful views, as I say. So how does the view that you have managed to produce differ from that?
Well, since the crater opened up about 4 years ago, one of the biggest hazards they've had to contend with here are rock falls from that crater wall landing in the lava lake and producing some fairly impressive explosions.
We've actually got some footage of those rock falls falling, and it is, as you say, quite dramatic. Let's just have a look here. Yeah. So that is one of the biggest risks of this particular crater, is it?
It's true.
Okay, so from your map that you've produced, which I think we can have a look at, what has that told you? If you can talk us through it, because it's a little bit confusing.
Here's the active crater right here.
Yeah.
And we took this image back in February, and again a couple days ago.
Right.
So this image from February shows the crater walls here, and as it pans around, you'll be able to see into the crater.
So this is the lava lake.
Lava lake is down here, and what we've noticed from February to today is that the level of the lava lake has gone up about 20 meters, and that parts of the crater wall, especially down here, have widened substantially as rocks have fallen in. So we're just trying to get an idea of how this crater works so that the Park Service and HVO can use that information to make more informed hazards predictions.
And is there anything that you've noticed? I mean, you say that the lava lake has risen 20 meters. Are there any other features that have kind of alerted you?
When we first saw this image, the thing that really jumps out is something you're going to see in a second, is this rock ledge right here.
Right.
As it turns, you'll see that it's overhanging the lava lake by about 30 meters.
Wow.
Now, when you look at that, it's like, well, that's potentially a problem. On the other hand, it could remain stable for a long period of time. It could break off in sort of a piecemeal fashion. We don't know yet, so our research is based on trying to come to a better understanding of what's going on in there.
But presumably this very accurate mapping, I mean, it is extraordinarily detailed, isn't it? I mean, literally being able to pick out areas of rock is giving you and the people here a much better understanding of that crater.
Yeah, when you put these detailed views in the context of the history that the field geologist goes out and accomplishes, it allows for some more informed predictions that the USGS and the Park Service will put out. We just try to provide some information and some science and ask and answer questions that could help.
Thank you very much indeed for joining us today, Steve. Well, the more we study volcanoes, the more we do know about them, but the one thing that we definitely know is that if they choose to erupt, there is nothing we can do to stop them. And how big can those eruptions be? Well, Ed Byrne went to investigate.
The bright sun was extinguished, and the stars did wander darkling in the eternal space, rayless and pathless, and the icy earth swung blind and blackening in the moonless air. Morn came and went, and came, and brought no day. And men forgot their passions in the dread of this their desolation, and all hearts were chilled into a selfish prayer for light. Cheery stuff. Lord Byron wrote those words in July of 1816. In inspired by The Year Without a Summer. What Byron didn't realise was the reason that the weather was so unremittingly bad that year was because the year previous to that, Mount Tambora erupted off the coast of Indonesia, the largest volcanic eruption since records began. Which begs the question, how does a volcano erupting thousands of miles away have such a marked effect on the weather in Europe? Well, it's all about the way volcanic ash plumes spread out through the atmosphere. Dr. Jeremy Phillips from the University of Bristol specialises in ash plumes and is on hand to explain. To represent the Earth's atmosphere, he's filled up a tank with salt water, with dense water at the bottom and less dense water at the top.
What you can see is a plume source, and that's going to represent a volcano like Tambora erupting. The plume rises up, the mixture then finds a level in the tank where it's the same density as the fluid in the tank, and then it can't rise any higher and it starts to spread out across the tank. And this is essentially what happens with volcanic plumes in the Earth's atmosphere. Typically this level is somewhere between 15 and 25 kilometres high in the atmosphere.
The density of the lower air forces the plume up until it finds a lower density air, and then it just spreads out right across.
And you can see these large clouds can spread until they circle the whole globe.
When Iceland's Eyjafjallajökull volcano erupted in 2010, the resulting ash plume covered most of northern Europe. By comparison, the eruption of Mount Tambora was around 1,000 times bigger. Its ash engulfed the entire world. In what became known as the Year Without a Summer, the ash blocked the sun's rays, causing climatic extremes that not only inspired Byron's poem, but brought famine and death to tens of thousands across the globe. Here's what's left of Tambora today, a gigantic crater 3 miles across. But there are other volcanoes out there which make even Tambora look like small fry. This is Yellowstone National Park in America, and it's the size of a so-called supervolcano. Incredibly, the entire park sits inside a giant supervolcanic crater, or caldera. It's nearly 60 miles long, more than 30 miles wide, and it last erupted over 600,000 years ago. Scientists think that there are at least 50 supervolcanoes on the planet. None have gone off for at least 26,000 years, so it's difficult to imagine just how immense these eruptions must be. Dr. Jenny Barclay, a volcanologist from the University of East Anglia, has some explosive experiments to give me an idea. The first involves a film canister, milk, food dye, and Alka-Seltzer. That's pretty good. Pretty good. I'm hoping that wasn't supposed to be a supervolcano, though.
No, and this is one that we would call VEI1. So VEI is Volcanic Explosivity Index, and that is a 1, and it goes from 0 up to 8.
Okay, 0 just being lava. Right,
yeah.
Okay.
So this one is just a little Hawaiian type of explosion, quite small compared to a supervolcano.
Well, that's a 1. It goes up to 8. 8 being a supervolcano then.
That's right.
And here, representing a number 8, we have a bin. What are we using in here?
Well, what we've done is we've filled the bin full of water, and that's going to be some of our magma. We're going to put some lovely coloured balls in to be broken up magma coming from our explosion.
We're using this contraption?
We are indeed using this splendidly made contraption, which basically allows us to put a little bit of liquid nitrogen into the bin.
Liquid nitrogen! Yes!
Okay, so what we need to do is put our safety gear on.
Radio. Like that I've had to take my glasses off and put glasses that are only slightly nerdier looking on.
Oh, you're part of the gang now. So I will pour in the liquid nitrogen,
Right.
and it's going to turn into a gas and pressurise this and cause an explosion, which is going to drive up and give us a sense of the difference in size between these two types of eruption.
And it gives me a chance to play with liquid nitrogen. Let's retreat to a safe distance. And there's a supervolcano. That was beautiful. That was quite a beautiful and colourful portrayal of a global catastrophe. When Mount Tambora erupted, it threw out over 50 cubic kilometers of volcanic material. But a supervolcanic eruption could erupt with well over 1,000 cubic kilometers. That amount of ash could trigger a long and sustained volcanic winter, which could last years, if not decades. And if we were really unlucky, plunge Earth into a new ice age.
Yeah, what are the odds of one of those erupting?
Eruptions of this kind of magnitude, the supervolcano, typically go over hundreds of thousands or millions of years. So there will be another super eruption, but the likelihood, chance of it happening over our lifetime or our children's lifetime is vanishingly small.
It's a lovely film, but for me, I mean, I know this is going to get the tweets and emails going, but I don't think we should get too fixated about Yellowstone or any other supervolcano, because they happen so rarely, and there's nothing we can do about them. But the thing that we've seen this week is that active volcanoes are scattered across the planet, and in many of them, they're right beside huge population centres. And for me, what the attention should be is taking the science that we've demonstrated this week, that we've got now, and applying it around the world to those places to save lives.
Well, you can still get your questions in. Professor John Blundy is standing by via our website, bbc.co.uk/Volcano Live.
And for us, we've come to the end of our time here at Hawaii, but just time enough to thank the scientists from the Hawaiian Volcano Observatory.
And, of course, all the staff here at the Hawaii Volcanoes National Park who've made this all possible. We should also thank Madame Pele for giving us such a beautiful final day. And, of course, we need to thank you. Thank you for all your questions, your tweets and your contributions. It has been a really wonderful week, and we would just like to leave you with shots of Hawaii in all her glorious volcanic splendor, because when she puts on a show, my goodness, we've seen it this week, haven't we? It is something that will just make you realize that our Earth really is truly alive and truly dynamic. Goodbye.
Bye.